Hi, I want to talk about how the ideal gas law is a byproduct of applying Newton's second law to gases, but doing it many times rather than just dealing with the one, two, or maybe three objects that we typically deal with in a physics problem. So, our system is an ideal gas system in a sealed container where there's no heat exchange through the walls. So, under those conditions, any collision that happens is going to be an elastic collision. And what we're going to assume is the gas is really dilute. So most of our collisions are going to be between the molecules and the walls of the container, not the molecules with each other. So if we wanted to figure out what pressure we would experience based off those collisions, we can start by using impulse and momentum with one gas molecule to figure out how much force and then start scaling up from there. So each molecule is going to be indistinguishable and identical. And that is one of the key facts of this. So we're going to say that an individual molecule would have a mass of a molecule m0. And it has a momentum that's going to be randomly oriented, but if we take a look at, say, the wall that's pointed towards the positive x direction, those gas molecules are going to collide with that wall and rebound, and the only change in momentum would be in the negative x direction. And because it's an elastic collision between an object that's practically no mass compared to the walls of the container itself, our change in momentum should be roughly -2 times the mass of that molecule times the speed of that molecule in the x direction, because the y and z components of the velocity remain unchanged. Now, the time between collisions would be calculated, since there's no force other than that collision force. We should just say that the speeds would be uniform in all of the directions, so the average time between collisions, that molecule would have to travel back and forth across our box, which I'm going to say each side has a length of d, so it would be a distance of 2 times the length of the box, divided by the speed in the x direction, is going to give us the average time between collisions for that one molecule. So each molecule would contribute a force of the mass of the molecule times its speed in the x direction squared divided by the distance, because the factor of 2 on our change in momentum and the factor of 2 we have in delta t cancel each other out. Now, in reality, it's not a single molecule we're dealing with. We have many molecules. So if we wanted to calculate the total force, then what we would have to do would be to sum from our first molecule up to our nth molecule of all of those forces happening along that wall. So since they're all identical, they would all have the same mass m0. We'd be dividing by a distance d because the size of the container is the same for every molecule, but we might potentially have different speeds in the x direction. So what we would do is take the speed in the x direction of each molecule, square it, and sum up that value. Well, this is almost the definition of the simple mean of the speed squared. If I were to take the sum of the speed squareds for each molecule from I equals 1 to n and divide by the total number, that would be the average of the speed in the x direction squared. So what this is then, this quantity is the number of molecules times my average speed in the x direction squared. So I could rewrite my net force as saying the net force is the mass of a molecule times the total number of molecules times the average speed in the x direction squared, or let me rephrase that very carefully. It's not the average of the speed squared, it's the average of the square of the speed. We're squaring the speed first, then we're averaging it. Now, Really, if we want to look at the ideal gas law, we need to figure out what's going on with the pressure. Well, pressure from the ideal gas law, we said, should be equal to the number of molecules times Boltzmann's constant times the temperature divided by the volume. Well, pressure is also force over area. So if I take my force and divide by the area, so if this is a cube, the area would be d squared, and I would have d cubed in the denominator, which would just give me my volume. So my average pressure is going to equal the number of molecules, so we've got 1/4 of the things we're looking for, divided by the volume, we've got half the things we're looking for, times the mass of a molecule, times the average of the square of the speed. Now, if I want to take a look at what's happening here, that's almost a kinetic energy. The kinetic energy in the x direction would be 1/2 times the mass of the molecule times my speed in the x direction squared. So if I'm looking at some constants, then this quantity right here, 1/2 times the mass of the molecule times the average of the speed in the x direction squared, that would be my average kinetic energy because of motion in the x direction. Now that gas is free to move in 3 directions. So there would also be kinetic energy from motion in the y direction and kinetic energy from motion in the z direction. So if that motion is truly randomly distributed, then each one of those directions should contribute equal amounts of average kinetic energy. So my average total kinetic energy would be 3 times my average kinetic energy in that x direction. Well, if I make use of that fact, then this mv squared with the subscript x could be replaced with just the average of the speed squared as a whole. So square the speed of every molecule, average that together, and then I would have to divide by 3. And to get this 1/2, I can multiply and divide by 2. So that tells me then that my average pressure would be 2/3 times the number of molecules divided by the volume times my average kinetic energy per molecule. And now we are at what we call the thermodynamic definition of temperature. For the case of an ideal gas, because there's no other reactions other than those collisions, there's no source of potential energy, this kinetic energy is the energy of the gas, period. So what that means then is 2/3 times my average kinetic energy as a whole would have to be equal to, according to the ideal gas law, Boltzmann's constant times the temperature. And our average energy per molecule, which is the average kinetic energy, would be 3/2 times Boltzmann's constant times the temperature. And the 3 here comes about from the fact that we have 3 dimensions where we're free to move: x, y, and z. And there's a theorem in thermodynamics called the Equipartition Theorem. And what the Equipartition Theorem states is, for every degree of freedom, for every unique way that an object can move, we add in a factor of 1/2 times Boltzmann's constant times the thermodynamic temperature to the total energy of a gas. So in the next case, if we go beyond linear motion, we could have rotational motion. For each rotational degree of freedom, we would add in a factor of 1/2 times Boltzmann's constant times temperature. So we can have at most 3 axes for linear motion, 3 axes for rotational motion. That would give us 6/2, or 3 times Boltzmann's constant times the temperature. We could also have vibrational motion, depending on the setup of the molecule, and for every unique mode of vibration, we get another factor of 1/2 times Boltzmann's constant times temperature. So as gases become more complex, there's more energy associated with that gas, but it's all based off our thermodynamic temperature. So for PV to equal the number of molecules times Boltzmann's constant times the temperature, our definition of thermodynamic temperature is that for a three-dimensional gas, the thermodynamic temperature would be 2/3 times the average kinetic energy per molecule divided by Boltzmann's constant. Thanks for watching.